Uh-oh, don't like that. Okay, so a few things to learn today. The first is going to be the concept of a rate. We'll talk about rates first, okay? Well, a rate is the measure of some value with respect to time. So a rate that you're probably familiar with would be like your rate of pay. You might get paid $9.50 every hour, okay? So this is a rate. The rate is the amount of money, and this is how much you get every hour. Does that make sense? Okay. Another rate that's going to be important in the kinematics unit is the rate of change in displacement. Okay, so the rate of change in displacement. And that's like fancy talk for basically saying velocity. Okay, so the rate of change in displacement is called velocity. For example, if you were traveling 100 kilometers per hour, okay, what that means is every hour you've displaced yourself another 100 kilometers. Does that make sense? Okay, so let's try and solve a quick rate problem in terms of rate of displacement. Okay, so find the velocity in the following. Alrighty, so I'm going to draw a little number line here to start off. Love the number line. Okay, go. Put a little spot called the origin. We got 1, 2, 3, 4, 5, 6, 7, 8. That's probably good enough. We have negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's say we have an object. I'm going to say that it is a bunny rabbit. And I have to figure out something new to draw besides bunny rabbits. But for now, it's bunny rabbits. Okay, and let's say that the bunny rabbit goes for a little hoppy hop, and its initial position, you call it PI or P1, doesn't really matter what you call it, but it's 5. And then the bunny hops all the way over here to, I don't know, let's go to negative 7. I feel like this is a really good bunny. So instead of like, you know, redrawing it, if I just lazily work some magic here, I say something like group and clone it, and then my bunny just like comes over here. Look at that. It's like cheating, but not really. Oh dear. Okay, so now this bunny is over here. What did I say? Negative 8? Negative 7. So the F, its final position, is negative 7 meters. So far, so good. Is this a negative or a positive displacement? Which one? It's a negative displacement. Excellent. Now the next thing we need to know is we need to know how much time this took. Okay, so let's make up some time. Let's say the initial time in this scenario was like 6 seconds. Okay, so we don't start timing till 6 seconds. Could we ever have a final time that is a lower value than 6? No. Unless this bunny like has a flux capacitor on its DeLorean and it can go back in time, we have to have, I know, we have to have a time that is later than 6 seconds. So why don't we make it 16 seconds? just to keep the math simple. Okay. Well, the first thing I want to do is I want to solve for the change in displacement. And we know the displacement that this guy has from his initial position to his final position is his final position minus his initial position. Okay? And his final position is negative 7 meters. And his initial position is 5. So what does that give us? Well, 5 to there, plus 7. 5 plus 7 should be 12, but in the negative direction. So negative 12 meters. Awesome. Okay, now let's do a delta t to find out what time has passed during his hopping. So 16 seconds is his final, minus 6 seconds should give you 10 seconds. Okay, so two numbers. This is his change in displacement, and this is how long it took. Can we figure out what his velocity was from this information? So let's define what velocity is. Velocity, we said, is a rate, and it is the rate of change. Okay, so it's the rate of change in displacement. So we have to have delta d divided by delta t for whatever time interval it took. We've already sorted out what these are. So it's essentially negative 12 meters in 10 seconds, or the bunny must be going negative 1.2 meters every second. By the way, I'll just let you write that down and then we'll chit-chat. Okay, so just one more note here on notation. So units here, meters over seconds written like that, is sort of how we tend to want to do, like, write the units. But there's actually a way that I would prefer that you use. And essentially what that is it's meters times the inverse of seconds. Okay? You will find that when you go forward in physics, you will see meters per second written like this more often than not. It's the preferred way. Okay? One of the reasons why is because lots of times in physics you have units that are essentially made up of multiple different input units, if you want, and sometimes there's like multiple things underneath the fraction or as the denominator in the fraction, and it can become like mighty confusing when you have all kinds of stuff underneath here. So a way to get around that is to use this symbology, and all that means, right, is I don't know if you have done exponents much in math class yet, but you know, let's see here. Let's say we have, I don't know, something divided by 2. I don't know, 10 divided by 2. That's the same as saying 10 times 1 over 2. Do you agree with that? These mean the same thing? 10 divided by 2 and 10 times a half is the same thing? Well, it turns out that if I take 2 and I raise it to the power of negative 1, that's the same thing as this. Is that right? Let me double check. So, just to close the book on this, in case I write it that way, this is the same as saying meters per second, but this is sort of the more international way of doing it. Okay, good enough. Now let's just investigate displacement a little bit more, because sometimes you can find incidences of displacement where it can be a little bit confusing. Like, for instance, what happens if we go back to our bunny here? I'm just going to grab his little number line, if I can. And I'm going to say that instead of just traveling in one direction along here, what would happen if the bunny did all kinds of crazy things? Okay, so here's the observer watching some action from the origin. Okay, and let's say that the bunny rabbit starts here, and I'll just use a different color, starts here, and goes this way. Okay. how far did it go? Well, it went -6, or its displacement change was -6. Then let's say it went back this way. Call this I. And its second motion is back this way. Okay, so that's 6. So that's 1, 2, 3, 4. So it went now 4 to the right. And then let's say it went back over to here. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9 to the left. So first things first, okay? From where the bunny started, what is the bunny's total displacement? Well, does displacement care whether the bunny went back and forth, or does it only measure the difference between where it started and where it finished? Which one? Right. What measures the whole amount of land covered? Is it displacement or is it something else? Something called what? Also starts with a D. Right. Distance. So let's just look at here at this bunny and let's just distinguish between distance versus displacement. So distance is what we're kind of all familiar with. So if we look at the distance of the bunny, distance doesn't care about negative and positive, so it went 6 plus 4 plus 9. 6 plus 4 is 10 plus 9 is 19. The bunny covered 19 meters, but its displacement is simply the distance, sorry, that's wrong, the difference between its initial position and its final position. So what's its total displacement? Right, -10 meters. The bunny's in the same spot. These values are both associated with the same motion. One will give you a velocity when you do it over time, and one will give you a speed when you do it over time. Okay? So let's say this motion of the bunny took 10 seconds. Okay? Well, if it took 10 seconds, okay, we can then look at speed as being equal to distance over change in time. So that's 19 meters divided by 10 seconds equals 1.9 meters per second. Notice no positives or negatives. And then, similarly, we can find the velocity. Sometimes drives people bananas because it's weird, but that's displacement, or delta D over delta T. And sometimes to indicate, by the way, and you might see this, that this is actually a vector value, you may see a little arrow on top, okay? So if you ever see a little arrow, they don't mean distance, they mean speed, okay? I'm sorry, I said that wrong. They don't mean distance, they mean displacement, okay? So we've got -10 meters divided by 10 seconds, or -1 meters per second. This is a velocity, it's a vector. This is speed. It's scalar. Does that make sense? So I'm just going to say a word about graphs here. And the type of graph we're going to talk about is the displacement time graph, or displacement versus time graph. Really what it actually is, although it's called a displacement versus time graph often, is really a position versus time graph, okay? And I just want to talk a little bit about general graphing, okay? We're actually going to have to do some work with this. We're just going to talk about some good general graphing habits, because lots of times people make some interesting choices when they're doing a graph, okay? So say we have that, and say we have this. Okay, and let's say we have, you know what? Let's look at this this scenario up here. Okay, so we could take this and we could do a position versus time graph with this information. Just give me 1 second to pull that down. So let's write down what we have here, and then let's put this on a position versus time graph. Does that make sense? So let's say at the start, time equals 0. Okay. We have a position equal to 5, okay? Now remember, the whole time is 10 seconds. So I'm going to make up some information, and we'll see if we can work out how that's going to work. Okay, so let's say after 3 seconds, the bunny is now here at this spot. So 3 seconds, his position is at -1. Right? He's gone -6, so his position is at -1. So we can put time and we can put position here. Okay, so say at 6 seconds, the bunny's over here, and that was at 4. And then at the end, we'll say time equals 10 seconds. The bunny is now at -5. Okay, so here's the information that we're interested in putting onto a graph. See how we go about doing that. So I'm just going to grab this stuff, and I'm going to bring it down. And then we'll put it into our graph that's waiting for us over here. All right, so the first thing we got to do with the graph is we have to make the graph have the numbers that we want. So it looks like the highest value that we have in the positive is 5. And we have some negative here. This makes it a little bit tougher. You got to actually have a graph that looks like this because it needs to extend into the negative values. Okay? So bear with me here while we sort this out. Okay, so highest in the positive is 5. So 1, 2, 3, 4, 5. Highest in the negative is -5. 1, 2, 3, 4, 5. This axis is representing position. And the units we said was meters. Okay. This axis represents time. It goes for 10 seconds. So and since we're not using the rest of the graph, why can't I erase that? Come on. I can probably shrink it. There's always a way, right? Okay, so let's start plotting information onto our graph. Time 0, the bunny is at position 5. So right there, okay? That's where it starts. Remember? If you can't remember, just roll up and take a look. There it is, over at position 5. That corresponds to here on our position time graph. This is, of course, 0, -5, and +5. Okay? Then, after 3 seconds, or at time 3, 1, 2, 3, the bunny is now at -1. So there it is. Then at 6 seconds, the bunny is back up to 4. Okay? And then at 10 seconds, the bunny is all the way down here at -5. So, if we want to get a picture of the motion of the bunny, what we can do is start to connect up these dots. So first it traveled left, then it traveled back to the right, and then it scooted on down to the left to its final position. Of course, our graph has to have a label. And that label is position versus time. And we need to label this axis. It's time, and it's measured in seconds. Okay? So what we've done is we've made a visual representation of the motion of a bunny on a graph. Are there any questions? Next time we'll talk about what this slope represents. Does anyone have an idea as to what the slope of this graph might represent? Have you done slope in math class yet? Rise over run? So in this case, our rise is -6, and it happens in 3 seconds. Displacement change over time change gives us what value that we just learned? Well, something to think about anyway. What might slope represent here? Okay, and that's where we'll stop for today.